Assalamu alaikum dear students. I welcome you to 27th lecture of probability and stochastic processes. In previous lectures, we have almost completed our discussion of transformation of random variables, where the underlying unpredictable experiment gives out a value which we can observe directly, but sometimes we are interested in a transformed value. Rather than working with directly observed value, we modify it and then analyze the behavior of the modified quantity. The modified quantity is also unpredictable and we call it a derived random variable. So from an underlying random variable which is directly observable, we work with a new random variable which we call derived random variable. There were many examples that we discussed. The first was where we transformed a scalar valued random variable to another scalar valued random variable through a transformation which was a function from R to R, from set of real numbers to set of real numbers. Such a function is like y is equal to g of x. So it takes a number x and gives you a number y, and g could be any function: square root of x, square of x, sine of x, 2 times x, etc., etc. We covered that case, and from that case onward we moved to the case of two random variables, two underlying random variables, where the random experiment gave us two observations. We call one the underlying random variable x, we call the other underlying random variable y. We combine these two observations of x and y through a function and get a scalar valued random variable, a new random variable we call z. So z is a scalar valued random variable which attains its value based on values of two underlying random variables x and y. So the transforming function is of kind z is equal to g of x comma y. So this transforming function is from r square to r. It takes two arguments, value of random variable x and value of random variable y, and gives you a new value which we assume to be the value of new random variable z. And the third case we discussed was where we found two new random variables from two underlying random variables. There was random variable x and random variable y directly observed from the random experiment. We combined these two random variables x and y through a transformation g to get a random variable u. Then we combine the two values through a transformation h and get another value v. So from two underlying random variables x and y, we got two derived random variables u and v. We analyze the behavior of these two random variables by working with their joint PDF. As we analyze the behavior of a single scalar valued random variable through working with its PDF. So the PDF of derived random variable is the quantity that we want to reach at. And in our discussion in previous lectures, we followed two routes to reach that. The first route was where we found the CDF of the transformed random variable first, and then we took the differentiation of that CDF to get to the PDF. And the other route was kind of direct route where we studied the transforming functions and how they modify the domain of underlying random variable or variables to derived random variable or variables. And from this relationship, we directly reached to the joint PDF of derived random variables from the joint PDF of underlying random variable and the nature and characteristics of the transforming function or functions. The two routes I just described were applied to two cases. In the first instance, it was applied to transformation of scalar valued random variable x to a new scalar valued random variable y. And the other case where both routes were applied were the transformation of two underlying random variables x and y to two new random variables u and v. For the case of transformation of two underlying random variables to a single scalar valued random variable through a function z is equal to g of x and y, a function which is from r square to r, was obtained through only one route, and that was through CDF. So if we have to transform a joint PDF of two underlying random variables x and y to a new derived random variable z, a scalar valued random variable, through a transforming function which is a function from r square to r, then we can only take this route where we find the CDF of z from joint PDF of x and y, and from that CDF of z we reach the PDF of z through differentiation. There is no direct path from joint PDF of x and y to scalar valued PDF of z. Why is it so? Let's have a look at the relationship of underlying random variables, the transformed random variables, and the transforming functions as they are applied to the case of transformation of scalar valued random variable to scalar valued random variable, transformation of two underlying random variables to two derived random variables, and the transformation of two underlying random variables to a single scalar valued random variable. Let's have a look first at the transformation of a scalar valued random variable to another scalar valued random variable. This is the unknown PDF of transformed scalar random variable y, fy of y. This is unknown. If we want to find the value of this unknown PDF at a certain point y, we formed an event by taking another point at y plus dy, and this is the probability of this event that y belongs to this interval. These 2 points were inversely mapped to point x1 and x1 dash. They are here. So when random variable x belongs to point x1 or to any point between x1 and x1 dash, the random variable y belongs to this. So probability of this event, shown in red, is equal to probability of this event. And they are related through this inverse mapping which maps y to x. By equating the probability of this red event with probability of this blue event, we were able to find the probability of new transformed random variable y in terms of the PDF of old underlying random variable x and the slope of this inverse mapping at this point y, actually the absolute value of this slope, because at this point slope is negative, but we used the positive value, the absolute value of this slope. An important assumption in this case is that if you take this point y and this y plus dy very close, that is dy is very small, much smaller than 1, then this interval is an interval on real line. And this is such a small interval that this PDF from this point to this point does not change much. If that's the case, then so is the case here, because slope is not infinity or 0. So if these 2 points are close, these 2 points are also close. And important thing is that this interval is small, this interval is small, and we can assume that during this interval the PDF of y does not change much, and during this interval the PDF of x does not change much. This is a very important assumption which we are going to rely upon heavily. Let's have a look at another case of transformation of scalar valued random variable to another scalar valued random variable. In this case, the mapping is non-invertible. This is the original mapping G which transforms x to y. And in this case, this is the unknown PDF of y and this is known PDF of x. Again, we form a small event which covers the values of random variable y from y to y plus dy. This is a very small interval of width dy, with again that assumption that during this interval the unknown PDF of y does not change much. It remains the same during this interval of width dy. These 2 points y and dy on y-axis get inverse map to 2 intervals from x1 dash to x1 and x2 to x2 dash, and these 2 intervals are here on the PDF of x. So if this interval is small, because of these finite slopes, these intervals are small and these intervals are small. So we can again assume that PDF of x does not change much when x varies from x1 dash to x1. This interval is small. Similarly, the PDF of x does not change when x changes from x2 to x2 dash. This interval is also small. So PDF is flat during these 2 intervals, and by using this assumption, we can find the probability density function of y in terms of probability density function of x and this non-invertible mapping. The same is true for the case of 2 underlying random variables giving us 2 derived random variables. In that case, we find the joint PDF of 2 new derived random variables u and v from the joint PDF to underlying random variables x and y by observing the nature of transforming functions g and h. And we used that transforming functions and their Jacobian to come up with a direct formula for joint PDF of u and v in terms of joint PDF of x and y. Let's have a look at the first transforming function, which is invertible. In that case, this is the UV plane where the joint PDF of 2 derived random variables u and v will be defined. To find this unknown joint PDF of u and v, we take a small rectangular region on UV plane. So this is an event, and probability of this event is the integration of joint PDF of u and v over this rectangular region. We assume that this rectangular region is very small. This dimension, which is dv, and this dimension, which is du, are both much smaller than 1, and during this rectangular region, the joint PDF of u and v, which is a surface defined over this UV plane, remains flat. It does not change much when we move over this rectangular region. This rectangular region gets mapped to this almost parallelogram region through inverse mappings of phi and psi. And the assumption, the most important assumption that we are going to rely upon is that if this region is a small region, so is this region. If dv and du are much smaller than 1, and during this rectangular region, the joint PDF of u and v remains flat, so is the case here. Over this parallelogram region, the joint PDF of x and y remains flat. It does not change much. And then by equating the probabilities of these 2 events and the Jacobian of that inverse transformation, we were able to find an expression for joint PDF of u and v in terms of joint PDF of x and y and the Jacobian of transformation, the inverse transformation or the forward-going transformation, whichever you want to use. If you want to use the inverse transformation, the Jacobian of inverse transformation, that Jacobian gets multiplied. And if you want to use the Jacobian of forward transformation, then that Jacobian divides fxy to give you fuv. Let's have a look at the next case where the mapping from xy to uv is not invertible. In that case, the inverse mapping of this rectangular region gives us 2 regions in xy plane. And to find the unknown joint PDF of u and v over this uv plane, we again take a small rectangular region with both dimensions, height and width, much smaller than 1, so that it can be assumed that the joint PDF of U and V remains almost flat over this small region. And the inversely mapped parallelogram shaped regions, this and this, also have small dimensions, and it can be assumed that the joint PDF of X and Y remains almost flat over these two regions. With these assumptions, we can easily find the joint probability of U and V from the joint probability of X and Y and the sum of Jacobians of the two regions in XY plane which get mapped to a single, simple, small rectangular region on UV plane. In all these four cases, transformation of a scalar valued random variable to another scalar valued random variable through invertible or not invertible mapping, and the transformation of two underlying random variables X and Y to new derived random variables U and V through invertible or non-invertible mapping is the same. That if you take a small region in XY plane with small dimensions, so small that the joint PDF of X and Y remains flat over that region, then the mapped region in UV plane also is small, and you can again assume that the joint PDF of U and V over that region remains flat. This very important assumption usually fails when we are transforming two random variables X and Y to a scalar valued random variable Z through a transforming function of the form Z is equal to G of X and Y. Examples of such functions include Z is equal to X plus Y, X minus Y, X minus Y whole absolute value, X square plus Y square, etc., etc. So when the transforming function takes two values and gives out one value, then that assumption that if you take a small region in one plane and get a small region in the other plane or domain fails. Let's have a look at a simple example where we are transforming a joint PDF of X and Y to a new scalar valued PDF of Z. So the transforming function is of the form Z is equal to G of X and Y. It takes values of random variable X and random variable Y, processes these values through a function and gives you a value of Z. So suppose you want to find the unknown PDF of this scalar random variable Z, you again form a small region. Take point Z and take a point Z plus DZ. So this is a small region, very close to each other these 2 points are, and you can assume that this unknown PDF is flat during this interval of width dz. Now we have to find all the points x comma y which get mapped to this interval z to z plus dz. This mapping looks like a mapping of z is equal to x plus y. If that's the case, then this small interval gets mapped to a thin, narrow, infinite length strip. You can make this interval as small as possible, and so will become this width of the strip. Smaller the interval here, smaller the width of the strip, but the length of this strip will always be infinite. So can you assume that over this infinite length strip of very small width, the joint PDF of x and y remains flat? No, you cannot. If you are taking this small strip of very small width, then if you move this way on the strip perpendicularly from one long side to other long side, then the distance is small, and you can assume that during this interval, during this travel, which is along the 45-degree line, the PDF, the joint PDF of x and y does not change. But if you move along these long lines, then the PDF certainly changes, and you cannot say that you can equate one probability, which is the multiplication of width of z by the height of unknown PDF, and on the other side you can assume a constant PDF over infinite strip. Simply you cannot. Hence you have to rely on finding the probability of the event represented by long, thin, infinite length strip, and you have to rely on integration because things change when the domain is a long, narrow strip. Hence, if you are transforming a pair of underlying random variables to one derived random variable through a function which is from r squared to r, there is so much loss of information that you have to rely on that procedure where we first found the CDF of z through integration of joint PDF of x and y over these narrow strips or any other region which is warranted by the transforming function g, and then after this integration, once you have CDF fz, capital Fz, you can differentiate it to get to the PDF of z, which you can later on use to answer the unpredictable behavior of the derived random variable z. With this, I conclude my discussion of transformation of random variables, where behavior of unpredictable derived quantities was analyzed through behavior of unpredictable underlying quantities. Transformation of random variables x to y, from xy to z, and from xy to u and v. We analyze the behavior of derived random variables by working with their probability density functions. A probability density function of a random variable completely characterizes its unpredictable behavior. If you know the PDF, you can say many things about the behavior of that random variable. There are certain situations where you do not need such complete information, only a summary of the behavior of random variable is sufficient. Such a summary could be the mean value of random variable, the variance, the standard deviation, or other higher moments, both normal moments and centralized moments. So if you are only interested in such summaries of behaviors of derived random variables, then you don't have to find the complete characterization through finding the PDF of derived random variables. In that case, you can get to these summaries, these moments, by working with the moments or summaries of underlying random variables, or by working with the PDF of underlying random variable and the transforming functions. So if you know the PDF of underlying random variable, which you always know, and the nature of that transforming function, which maps values of underlying random variable to values of derived random variable, you can reach at the values of those moments directly by working with the PDF of underlying random variable and the transforming functions. Actually, we have worked with this case when we were analyzing the behavior of transformed random variable, a scalar valued transformed random variable, in terms of its mean and variance from the behavior of the underlying random variable. Let's have a look how these things are related to each other. So we are interested in finding the expected value of transformed random variable y, which is defined in terms of the value of underlying random variable x and this transforming function g. So if we are interested in finding the expected value of y, we can find it from the PDF of y. which is unknown. But suppose if this PDF were known, then all you have to do is integrate y times this PDF and you will have expected value of y, the transformed random variable. So how do you do that integration? You again take a small interval and assume that in this interval the value of PDF remains same, and then you multiply the value of this function y, this value y, with the value of the PDF, and you continue multiplying the value of y and the height of this PDF to get that integrand, and when you integrate that integrand over the whole line, you get the expected value of y. You can reach that expected value of y by working with the PDF of x. All you have to do is that look at this interval and look the corresponding interval on the x-axis. For this interval, when y is from y to y plus dy, the x lies from x2 to x2 dash. So what's the probability of this event? Is same as the probability of this event. When you multiply this with the value of y, you can reach this value of y by transforming this x2 through this mapping, this is inverse mapping, through this mapping G and reach this value. So this probability multiplied by this value is same as this probability multiplied by this value transformed through G to become this value. So you can find the value of expected value of y by working with the PDF of y, but instead of doing that, you can find the expected value of y by working with the PDF of x and the function which takes values of x, transforms them to values of y. In the form of the equation, the integral, these two integrals are shown on the plasma, and you can see that if you want to find the expected value of y or mu y, the first route is by working with the PDF of y. In that case, you multiplied y with the value of the PDF at this point y and integrate this multiplication over the whole range of y. But you can get the same answer by working with the PDF of x. So x takes on a value and you transform this value through this transforming function g. So here it is gx, which represents the value of y, and you multiply this with the value of the PDF at this point x and take this multiplication and integrate over the whole range of x. So both expressions give you expected value of y or mean value of y. Once you have found this, you can find the variance of y again through two routes. The first route is through using the PDF of y. So you want to find the variance of y. This is the form of the other term where you take y minus just found the value of mean of y, mu y, subtract the two, square this and multiply it with the PDF of y, take this multiplication and integrate over whole range of y. But you can reach the same answer if you want to work with the PDF of x. You take the PDF of x and multiply it with g of x, which takes the values of y. This mu y or expected value of y is a constant already evaluated through this or this. You take these two terms, subtract them, square them, multiply them with probability density function of x and then integrate over the whole range of x. Both routes will give you the same answer. Whether you work with the PDF of derived random variable or you don't want to work with that, you want to work with the PDF of underlying random variable, you can reach the answer if you are investigating the mean, the variance or other moments of derived random variable. Here are a few examples of simple transformations and how they give us the value of different moments of derived random variable in terms of moments of underlying random variable. The first example is where y, the derived random variable, takes on a value which is the value of underlying random variable plus a constant beta. So y is x plus beta. In that case, the expected value of y, the derived random variable, is expected value of underlying random variable x mu x plus that beta. And the value of variance of derived random variable is same as the value of variance of underlying random variable, because when you add something to a random variable to obtain another random variable, the mean gets changed. But when you are trying to find the variance, you are trying to find it by subtracting the value of mean. Hence, if you get your derived random variable by simple addition of a constant number beta, then the variance does not change. Let's have a look at the next example. If the derived random variable y is obtained by multiplying the underlying random variable with a constant alpha, then the expected value of derived random variable is alpha times the expected value of underlying random variable, and the value of variance of derived random variable is alpha square times the value of variance of underlying random variable. And lastly, when y is equal to alpha times x plus a constant beta, the expected value of y is equal to alpha times the expected value of x plus that beta, and value of variance of y is equal to alpha square times the value of variance of x. So for the case of these simple linear transformations, it's very easy to find the mean, variance and other moments of derived random variable in terms of mean, variance and other moments of underlying random variable, and the values of alpha and beta used in these linear transformations. If we are working with a pair of underlying random variables and we know their joint PDF, then we can use that joint PDF to find the mean and variance and other moments of random variables derived from that pair of underlying random variables. Suppose we are working with two underlying random variables x and y, and we know their joint PDF f x of y of x comma y. Then we can use this joint PDF to find the mean value of x. That is slightly different example, because x is one of the random variables and it is not a derived random variable, but it is a quantity which is a random quantity, and it's not the joint pair of random variables. So it's just one of them. The point is, you can find the values of mean and variance and other moments of one random variable x without finding the marginal density of x. Usually if you want to find the mean value of x, the variance of x or other moments of x, you need marginal density of x, which you can obtain from the joint PDF of x and y. But you can directly use the joint PDF of x and y to find the mean, variance and other moments of x or y, the one of them. How it is so? Let's see on the plasma. Suppose you want to find the mean value of x, mu x, and one route is that you know the marginal density of x, fxx. If you do, then you can integrate x times the marginal density of x, integrate over the whole range of x, and you will have your expected value of x. Now, this marginal PDF of x is shown here. Here, this marginal PDF of x is obtained from this joint PDF of x and y by integrating this joint PDF along y. So if you integrate this joint PDF along y, you get the marginal PDF of x. And this marginal PDF of x replaces this expression And when you expand this, there is one integral with respect to x, the outer integral, and there is one integral with respect to y, the inner integral, which gives us the marginal density of x. If you rearrange the terms and everything is nicely behaving, then you have a double integral of x times the joint PDF of x and y, and the double integral is with respect to x and y. And you can certainly change the order of these two integrals if you want to, because we are assuming that this expected value exists and everything is going to behave nicely. Similarly, if you want to find the variance of x, the first route is through PDF of x. And you take that PDF of x and multiply it with x minus mu x whole square, integrate with respect to x over the whole range of x, and you have the value of variance of x. Once again, if you replace this PDF of x with this expression, you get a double integral with respect to y and x in any order, and you multiply this with x minus mu x whole square times the joint PDF of x and y. So you can use the joint PDF of x and y directly to find the expected value of x or variance of x. Similarly, you can find the expected value of y and variance of y by using appropriate function here. Here you will use y minus mu y whole square, and here you will use y. So if you have joint PDF of x and y, you can use that to find different means and variances of x and y individually. By the way, if you have to find the correlation of x and y or covariance of x and y, you definitely have to use the joint PDF. But joint PDF can be used for other cases. Now let's assume that you have this joint PDF of x and y, and you want to find the mean or variance of a derived random variable z. And let's start with a very simple example that z is x plus y. For this simple example where z is x plus y, you can find the expected value of x plus y by using either PDF of z, where z is x plus y, or you can use the joint PDF of x and y in this evaluation. Let's have a look at this expression where we see that if we want to find the expected value of x plus y, where x plus y represents random variable z, because of linearity of this operation expectation, it's easy to see that this gets evaluated through this joint PDF of x and y simply by multiplying this with values of x and y. And if you open this, you can certainly see that this comes out to be expected value of x plus expected value of y. But if you have a complicated expression which relates values of x and y to values of z, then this g is that mapping, and if this g is this mapping, then expected value of z, where z is g of x plus y, can be evaluated directly from this joint PDF of x and y. All you have to do is multiply this joint PDF of x and y with this transforming function, which gives you value of z from values of x and y. If you use this expression, you will easily get a value which is expected value of transformed random variable z, where z is g of x and y. This function g, which relates x and y to z, can be any function. Suppose this is a function which relates x and y to give you one of the two random variables u and v, the u. So if g is a transformation from x and y to u, you can certainly find the expected value of u, which is expected value of this mapping g of x and y, and this can be evaluated by putting that g of x and y here, multiplying it with joint PDF of x and y, and taking the double integral over the whole range of x and y. Similarly, if you want to find the variance of this transformed random variable u, all you have to do is put the right expression here. Here is the value of u minus the mean value of u whole square, and if you take the expected value of this expression, you will get your variance of u. So you take that expression, multiply it with joint PDF of x and y, take the double integral over the whole range of x and y, and you have your variance of u. You can have variance of v and expected value of v evaluated using the appropriate expressions which are very similar to the expression shown on the plasma. The point is that if you want to just find the mean values, the variances and other moments of transformed random variables which you obtain by using mappings like G, H, etc., then you can easily find those moments, means and variances and higher moments, by using those transforming functions G's and H and the joint PDF of underlying random variables x and y. You can also use this idea to find the correlation and covariance between two derived random variables, assuming that that correlation does exist. If so, then the correlation between derived random variable u and derived random variable v can be found by this expression. RUV, the correlation is equal to u times v times the joint PDF of u and v integrated over the whole range of u and v. This is the original formula that you could have used if you had known the joint PDF of u and v. But if you don't know this, then you should try to see how u and v are related to x and y, which is already given that u is equal to g of x and y and v is equal to h of x and y. So by using this joint PDF of u and v and taking u and v here, you are actually trying to find the expected value of this u, which is g of x and y, this v, which is h of x and y, and when you are finding the expected value of this multiplication, you can use the joint PDF of x and y instead of joint PDF of u and v. And to use that, this expectation in terms of joint PDF of x and y comes out to be this one, where you take the double integral of g of x and y times h of x and y times the joint PDF of x and y integrated over the whole range of x and y. Here is a graphical representation which equates this evaluation with this evaluation. If you look at this evaluation and divide this whole UV plane into small rectangular regions of very small width and very small height, then this expression is equivalent to taking a value of u here, a value of v here, taking a small region width du, height dv, taking that area du times dv, multiplying with the value of the joint PDF at this point, multiplying it with the value of u here, with the value of v here, and adding all these values of u times v times value of u and v and du times dv. When you take that small rectangular region, its inverse map is here, which is a paralleloshaped region. Or if you take that paralleloshaped region, its map is here. This inverse map is through phi and psi, and this forward map is through g and h. So if you take all these rectangular regions and look at their maps, there will be all parallelogram shaped region which will cover the whole xy plane. So if you take that all parallelogram shaped regions, find their area and multiply that area with the known PDF of x and y and the values of u and v which are obtained from values of x and y here through g and through h. then this is exactly the expression we are looking for. If values of x and y here are whatever they are, then you transform these x and y to u through g, you transform this x and y to v through h, and then this area which is fxy dx dy and this area which is fuv du dv, they are the same, and this expression is equivalent to this. So if you want to find the correlation of two derived random variables u and v, you can find that in terms of the transforming functions g and h and the joint PDF of two underlying random variables x and y. Similarly, if you want to find the covariance of derived random variables u and v, you can use the expressions for g and h and the PDF of underlying random variables x and y to reach the covariance of u and v as shown on the plasma. So you want to find the covariance of u and v here, which is expected value of multiplication of two expressions. The first is u minus mean value of u. The other is v minus mean values of v. So if you multiply these two and take expected value of that, you can do that if you use the joint PDF of u and v. But if you just assume that these expressions are expressions of x and y transformed to u and v, then you can certainly use this expression, which is taking g of x and y for u, subtracting mean value of u, and multiplying the whole thing with h of x and y, which is equivalent to v minus mean value of v. Multiply these two, and now whole thing is a function of x, y transformed through g and h. So this function of x and y is multiplied with the joint PDF of x and y, and the whole expression is integrated over x and y, and you get your covariance of u and v through transforming functions g and h and the joint PDF of x and y. You can use this expression to find covariance of u and v no matter what is the nature of this transforming function g and the nature of transforming function h. Similarly, you can use the other expressions shown on previous slides. But if these transforming functions g and h belong to a special class of transformations called linear transformations, then it's very easy to actually find the value of different moments of u and v directly in terms of values of different moments of x and y. So if u, the value of random variable u is equal to alpha times x plus beta times y, so this is the kind of linear transformation which combines the value of x with value of y to give you a value of u. And similarly, this is the kind of transformation which combines the value of x and value of y to give you a value of v, which is equal to gamma times x plus delta times y. Then these transformations are special, simple, called linear transformations, and they can be collectively written in the matrix form, where this column vector or column matrix uv is the result of transformation of this column vector xy through this 2 by 2 transforming matrix. So you can see this u is equal to this row multiplied by this column. So u is equal to alpha times x plus beta times y, and v is gamma times x plus delta times y. So this pair of transformations, this is g, the linear version, this is h, the linear version. For these linear transformations, they can both be compactly written in the matrix form, where this column vector represents the two values of two derived random variables, and this column vector represents two values of underlying random variables, and this is a simple 2 by 2 matrix which takes the pair of values of underlying random variables and transforms this pair to the values of derived random variables. If your transforming functions are such simple linear functions, then you can use the results that I will derive in the next lecture to find the mean value of u, mean value of v, variance of u, variance of v, correlation of u and v, and covariance of u and v in terms of means, variances, covariances, correlations of underlying random variables x and y. This will be done in the next lecture. Till then, I wish you the best. Thank you. Khuda Hafiz.